In this section of the lecture on the I2C protocol, let's take a look at the 24LC515. It's a serial double EEPROM. From the videos page, we can simply go to the datasheet online to get more information about that part. Here on the first page, we have a handy pinout to give us an idea for the electrical connection of the chip. 3 address pins, a ground and power, write protect, and then the 2 I2C serial clock and serial data pins define the chip. Here's another diagram of the chip. Instead of drawing it pin by pin, there's a nice electrical layout. We see the clock and data lines connected to our PIC24. Remember, we have to have pull-up resistors because that is an open collector bus. Let's begin by just briefly discussing the pinout required in order to properly operate this part. Page 5 of the datasheet gives us a handy table to walk us through the pinout. One thing to notice, A0 and A1 are user configurable chip selects. A2 is not. This pin must be hardwired to the logical 1 state. Otherwise, it doesn't work. So obviously we need to do that. This also implies that A2 pin has a function that is not included in selecting its address on the bus, and we'll discuss that momentarily. Here on page 6 of the datasheet, we notice the standard I2C conditions, a start, data, and then a stop to define the bus. 8 bits of data are always followed by an acknowledge bit, so this is a standard I2C peripheral. Turning to page 7, a control byte is the first byte received following the start condition. We start with a 10-10 binary, a bit select bit, and then an A15, which corresponds to A15. So here's that diagram. The I2C address is always going to be a 10-10. B0 bit we'll talk about in a minute. A1 and A0 that correspond to physically that A1 and A0 pin on the chip. Flipping back to the first page, A0 is on pin 1, A1 is on pin 2. A standard I2C, 1 for read, 0 for write, and then the chip, if functioning properly, will return and acknowledge, and that defines our I2C address. Returning to the B0 bit, note that this bit acts as the A15 address bit for accessing the entire array. That is, we've got a 64K part, 64K bytes of storage. The topmost bit is selected with B0. The rest of the bits come down here at the bottom of the page where we send the lower 15 bits of the address, where the top bit, instead of being here, is actually stuck in here, the block select bit. So effectively what we have is a part with multiple personalities. There's 32K in the upper half and 32K in the bottom half of this part. It's as if the same package contains 2 separate chips. Moving on to page 8, let's look at actually writing data to the chip. We have several options. We can do a write of a single byte or write of a page. Here's the overview. Looking more carefully, here's a byte write. We begin with a start. We send that control byte. Remember, it's always a 10-10 followed by which of the 2 chips inside a chip, B0, followed by how you wired up the A1 and A0 pin physically, a 0 for that read-write bit since this is a write. Then we send the address of the place we're going to write, the high byte, the low byte of the address, 1 byte to be written to that location, and a stop. Let's take a look at a specific example. Let's say we decided to write 1010, a B0 bit of 0, and assuming A1 and A0 are both tied to ground, so we write zeros and a 0 for write, followed by a high byte of, let's say, 0001, 0010, and then a low byte of 0011, 0100, and then let's write some data out there, 0110, 0111. If we wrote that data, let's go through and think about what that means. First of all, what we'll find, let's translate that to hex just so we're on the same page. Of course, that's an OX A0 and OX 12. Here's an OX34, and here's an OX67. What have we done in writing that data? With A0, we started the transaction, specified a write, and we gave the upper bit, the address bit 0 here, is then stuck right in here in terms of the effective address. So where did we write to? We wrote to address 1234 in memory. So the write was to address 1234 in the memory, and we wrote the data value 67 there. That's one quick example of how a byte write starts. A second option is to do a page write. That is, we can send up to 63 additional bytes beyond that first byte, and it'll be written sequentially to data. We do need to be page aligned. That means we need to start writing at the beginning of a 64-bit boundary and then write up to the end of it, and be careful not to cross that boundary. Again, let's take a quick example and think about performing that page write. Of course, we begin with the start. We send out the control byte. As before, let's do an A0. That means the B0 bit is set to 0. Now we'll specify that upper bit of the address. Again, let's write to 1234, and then we'll begin writing data. And for data, we'll pick something random, 0x00 and so on, 0x10 over here for a number of data bits. Again, what is the effect of those writes? What we've simply done is we've written to the address 1234 hex, and we've written data 00 there. The next address now has our next piece of data. Let's say we wrote 0x01 and so on and so forth. So again, the important part is here at 1234, that's our address where the data is written. Everything following that, here's what we've placed at 1234. The next little bit would be 1235. And the last data would be placed wherever we ended up. We could go up to 63 bytes forward from that starting offset. Now 1234 isn't page aligned, so we couldn't write all 63 without a wraparound, but this does serve as an effective example. Now, after performing a write operation, the device will then spend a certain number of milliseconds actually performing the write. That means we need to do some special testing to find out if the device is ready to receive a write. Here's the flow chart from the datasheet. We'll send that write command, for example, the single byte write or the page write we just discussed, send a stop to it. Then immediately we need to ask, is the write complete? We'll send a start, pretending that we're doing a write by setting the read write bit to 0. If we get an acknowledge back, that means the device is busy with the current write and it isn't ready yet. If we do get an acknowledge back, then we can begin our next operation. Turning to page 3 of the data sheet, note that the write time is significant. In fact, to write data to that EEPROM takes 5 milliseconds. So that write polling operation is very important in terms of waiting for the write to complete. Now that we've discussed the write, let's take a look at the example code necessary to perform the write. We're going to follow this link and scan down to look at the specific code. Here's code that waits for the write completion. Remember that sequence from the data sheet. We'll set the read-write bit using the I2C WADDR macro, start it, send out that address but not require an acknowledge to come back, and stop it, and then see if we got an acknowledge or not. If there's no acknowledge, then we'll simply run through that loop again. If we do get an acknowledge, then we know the device is now ready to receive data. To actually perform a write, we'll begin by configuring the address. We'll take, for example, a 16-bit memory address and split it into the lowest 8 bits and the upper 8 bits. Next, we'll go ahead and save those low and upper 8 bits to be sent as the first and second bits to be transmitted to the chip. We'll also take a look. Is the most significant bit a 1 or a 0? If it's a 1, then we need to set the B0 bit of the I2C address. We'll wait for the write to be completed, and then we'll simply write in bytes. The first 2 bytes of that buffer are the high and low bytes of the address to write to. The remaining bytes, block size plus those 2 extra bytes for the address, then form the data of that write. Now let's take a look at reads using the serial EEPROM. So here we are looking at read operation, and in particular, notice the rules. The part contains an address counter. That is, the way read works is that it reads the last word accessed. And it increments. If it reads one word, then the next thing you read will be the next word and the next word. So let's take a look at some of those implications in terms of how we read things. Now, for a current address read, that's fairly straightforward. We simply send a start as usual, the control byte, always a 1010, the B0 bit, A1 and A0. Now, of course, we're going to put a 1 in there for the read-write bit because this is a read operation, and then immediately we'll read 1 byte of data and then issue a stop to terminate the transactions. Now, this has one distinct disadvantage. The data we read is at the location we last wrote. That is, we didn't, in this transaction, get to specify an address we'd like to read. So obviously, we'd like to be able to perform a random read. And here we're going to use a little trick. Here's what we're going to do. First, we'll begin with a start, send a control byte, but notice we're going to send a 0 here. That means this is a write transaction. We'll send the high byte of the address, the low byte of the address, and then we'll actually stop and restart the transaction right here. With that stop and restart, we can then turn around, issue a read transaction. Notice we've got a 1 right there signifying a read, and then go on to read data at that address. So again, notice the pattern. First, a control byte claiming we're going to do a write, the high and low byte of the address to write, but before you write data, a stop and restart, and then we turn around and read the current address, which of course is exactly what we specified right here. We can, of course, also do a sequential read. It's the same basic idea, where of course we begin with pretending to do a write transaction and sending the high and low byte of the address, turning around and starting a read transaction. And of course, by read we mean we're using a 1 there as opposed to the 0 here indicating a write. After the read transaction, instead of simply reading 1 data byte, what we can do is request multiple data bytes, and the part can provide up to 32K of data before we then send the stop to complete that transaction. Now let's take a look at the example code here to operate the 24LC515, and specifically let's look at this read transaction. So here we are at the memory read function. You provide it with that I2C address, which, referring to the data sheet, of course, is the 1010 B0 bit, the 2 A1 pins on the chip, and that read-write bit. The 16-bit address within the EEPROM we'd like to write to, and a pointer to data to be written there. Now what we're trying to do is replicate in the data sheet this pattern of write, high byte, low byte, restart, read, and then read a series of data. Identical to the write transaction, first we begin by determining the low and high 8 bits of the memory address to be written, because those 2 low and high bytes need to be sent first and placed as the first 2 bytes in an I2C write transaction. Next, we'll look at the most significant bit of the address, and again, as before, we need to set the B0 bit. That's this bit right here, depending on whether we're in the upper chip inside the chip or the lower chip inside the chip. Just to make sure that a write is finished, a previous write is completed, we'll call that wait for write completion. Now remember our pattern based on the data sheet. Write 2 bytes, the high and low byte of the address. We see that right here where we send the high, then the low byte of that address. Then once we've done that, we're free to read back the same 2 bytes are first in that buffer, and the next 64 bytes following those first 2 bytes will then be data returned from that read. Now let's take a look at actually applying this read transaction in a program. First of all, we need to define the I2C address of the device. That's what this #define does. The A0 of the I2C address becomes, there's hex A, and then a 0, leave the B0 bit as a 0, pick whatever you've wired A1 and A0 to, in this case both are tied to ground, and leave the read-write bit as 0, and the code will automatically fill in both the read-write bit and the B0 bit, so only A1 and A0 should be set. That defines the I2C address. Next, we need to define a block size for testing. For example, you might reduce that to 4 to check smaller chunks of data. Right now we'll do 64, which is the largest amount of data that we can write at one point. Using that, we'll now take a look at the main code. Of course, we'll configure the chip, start up the I2C bus, decide whether to go into read or write mode. In the write mode, we'll simply input 64 characters, and then notice that we can simply provide a 64 character as an AU8 buff, provide it with an address to write it to, and of course the I2C address we decided on earlier for it, and the write is performed. Now let's look at a couple important features of that buffer. First of all, we began at location 2. Locations 0 and 1 are the high and low byte of the address, so we shouldn't use those. They'll be overwritten by that memWriteLC515 function. So we need to start at 2 and go to 64 plus 2, or block size plus 2, in order to perform that correctly. Now let's take a look at the read transaction. Very similar. We simply give it an address we'd like to read from, a buffer, and the for loop prints that out, and that concludes the code which composes this example. Note in this case, for the read transaction, because of the nature of a 2-byte write followed by a read of the current address, we can now index beginning at 0 to 64 for the read transaction. In contrast, the write transaction needs to begin at 2 and go up to 64 plus 2. And that's just the nature of, in a write transaction and only in a write transaction are we required to send the address high byte then low byte. And of course, read transactions, as we've discussed earlier, actually begin with a write, but just a 2-byte write, and then continue to that 64-byte read. This concludes the overview of the 24LC515. Thank you for your time and attention.